All right, go ahead and get out your notes. At the top, write Chapter 7, Exponents and Exponential Functions. We're moving into Section 7, Exponential Growth and Decay. All right, there are two important things that you guys need to write down. The first one is all about exponential growth. Exponential growth can be modeled by the function y equals a times b raised to the x power, where a has to be greater than 0 and b has to be greater than 1. The base b is your growth factor, which equals 1 plus the percent of change expressed as a decimal. So you guys probably want to write that down, which equals 1 plus the percent rate of change expressed as a decimal. Here's your equation labeled. A is your initial amount. The base, which is greater than 1, is your growth factor. And x is your exponent. Whenever you graph an exponential growth, you always have an increase. Okay, it'll never touch 0 on the x-axis, but it'll increase. All right, the next one is exponential decay. Exponential decay can be modeled by the function. Again, it's the same function, y equals a times b to the x. A has to be greater than 0, but now b has to be greater than 0, but it has to be less than 1. The base is still b, and it's your decay factor, which equals 1 minus the percent rate of change expressed as a decimal. Again, here's your equation. Y equals a times b to the x. A is still your initial amount. B is still the base as a decay factor, so you're going to take 1 minus the percent rate. And x is still your exponent. Notice now you have a decreasing graph, okay, that falls from left to right. And it gets close to x, or it gets close to 0 on the x-axis, but it doesn't ever touch 0. All right, now we're going to try some examples. Modeling exponential growth. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. If the trend continues, about how much will be spent at restaurants in 2015? All right. So first we want to set up our equation. Our equation is always y equals a times b to the x power. Remember, a is our initial amount. Our initial amount in this case is $360 billion. Y is what we want to find out. And b is going to be our growth factor. So how much it has changed. So we're going to actually have 7%. Since we know we're growing, we're going to have 1 plus our percent rate, which is 0.07, which equals 1.07. Okay, so we're going to have times 1.07 raised to the x power. Again, 360 is our initial amount. 1.07 is our growth factor using the formula that we got on the last page, raised to the x power. Now, we're going to use that equation to predict the annual spending in 2015. Okay, so we have to go from our original year and use 2015 and figure out how long has it been. Okay, so y equals 360 times 1.07. Well, from 2005 to 2015, that's 10 years, so we're going to put 10 as our exponent. And now we're going to solve that. You're going to get approximately 708, so 708. And that's just rounded to the nearest $1 billion. All right, next, if we are asked to express what is an expression that represents the equivalent monthly increase of spending at U.S. restaurants in 2005, we're going to take our 0.07, and this is monthly increase. Okay? We're going to take 1.07, and it's raised to the x power, and since we're talking about months, we have to do 1.07 raised to the 12x over 12, okay, because there's 12 months in a year. Now we have to break that up, and we have to do 1.07 to the 112 raised to the 12x. So all I did was split this up. And 1.07 is actually going to give you 1.0057. Okay? And since this is 12x, we're just going to say m because that's the number of months. So this expression right here will represent the equivalent monthly increase of spending at restaurants. All right, so let's try another one. This one says, suppose that in 1985 there were 285 cell phone subscribers in a small town. The number of subscribers increased by 75% each year after 1985. How many cell phone subscribers were in the small town in 1994? Then we have to write an expression to represent the equivalent monthly cell phone subscription increase. We are talking about growth, okay? So the first thing we have to do is use our equation. A times b to the x, okay? Y stays as y. What's our initial amount? Our initial amount we're starting with is 285 cell phones. We're going to multiply that by what is our growth factor? Well, growth factor, remember you take your percent, and we're going to take it and we're going to go 1 plus the decimal, which is going to give us 1.75. Okay? So that's our base, 1.75 raised to the x power. Now, what is x? Okay, well that's the difference, the amount of years. So from 1985 to 1994, how many years was that? Okay, so we're going to substitute the amount of years it was 9. And now we're going to solve it. Okay, and you're actually going to get y is equal to 43,872. Okay, so that's the first part they're asking you. That's how many cell phone subscribers were in a small town in 1994. But now they go on to ask you to write an expression to represent the equivalent monthly cell phone subscription increase. Okay. You're going to use your growth factor, 1.75. We're raising it to the x, but then remember we want it in months. So 1.75, 12x over 12. We're then going to find 1.75 to the 1 over 12, raised to the 12x. When you put 1.75 raised to the 1 over 12 in your calculator is going to give you like 1.045, something close to that. We're just going to round it. Okay? And remember, this becomes m. So there's your expression. All right, the next one. When a bank pays interest on both the principal and the interest an account has already earned, the bank is paying compound interest. Okay, compound interest is an example of exponential growth. So again, if they pay interest on both the principal and the interest on the account has already been earned, then you're talking about compound interest. You can use the following formula to find the balance of an account that earns compound interest. Okay, so everybody write this down. A equals P, parentheses, 1 plus R over N, closure parentheses, raised to the NT power. A is your balance. P is your initial deposit. Okay, your initial deposit, that's your principal. And then we automatically always have 1 plus. R is going to be the annual interest rate. You're always going to write that as a decimal. That's important. N, in both places, is going to be the number of times interest is compounded per year. Okay? So it's the number of times interest is compounded per year. And T is the time in years. All right, so let's try an example. Suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest compounded quarterly. What will the account balance be after 18 years? Okay, so the first thing you have to do is start by writing your equation, okay? So remember, we had A is equal to P, parentheses 1 plus R over N raised to the N T power. Okay, now we're going to plug our items in. We know that there is a principal of $2,000, so we can put 2,000 in place of P. We also know that there was a 4.5% interest rate, but that's as a percent. So as a decimal, we have to move our decimal 2 times to the left. Okay? So you're going to have 1 plus 0.045 over, since it is compounded quarterly, okay? Quarterly means 4 times a year. We're going to put 4 down here. We also have to raise it to the fourth power and multiply it by 18 because it was 18 years. Okay? So now we're going to solve this. The first thing I would do is probably multiply out here, okay, and then work in your parentheses. So we have 2,000. When we plug in 1 plus 0.045 divided by 4, we're going to get a decimal of 1.01125, and 18 times 4 is 72. And then we're going to multiply. We're going to raise 1.01125 to the 72 power, multiply by 200, and we're going to get a balance of $4,475.53 after 18 years. And that's how you would solve that one. All right, so let's try another one. Now it's going to say, suppose the accountant problem, the problem we just did, pays interest compounded monthly. So you're doing the same thing, only now it's compounded monthly. Okay, we know that in 1 year there's 12 months. So we have A is equal to, our principal was still 1,000. Okay, we still have 1 plus. Our percentage, our interest didn't change. So we have 0.045. Okay, we're going to divide it now by, since we're dealing with monthly, 12. We're going to have 12 up here, and the number of years didn't change. Okay? So now we have 2,000. 1 plus 0.045 divided by 12, all raised to the 12 times 18 is 216. And if we figure out what this is, we have 2,000. And we take 0.045 divided by 12, add 1 to it, you get 1.00375, all raised to the 216. And we are going to get a balance of $4,489.01. Tried to put my dollar amounts twice. Sorry, guys. All right, so make sure you pay attention to whether you're compounding monthly or whether you're compounding quarterly. Okay, annually would just be once a year. Okay, so that would just be 1. All right, now we're going to move on to some exponential decay, which is very, very similar to exponential growth. The only difference now is, remember, we have 1 minus. All right, so we're going to start with the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 100 meters increase in altitude, the pressure decrease is about 11.5%. What's the approximate pressure at an altitude of 300? Okay, so 300 meters. So first we have to write our equation. Y equals A times B to the X. The equation's the same as exponential growth, so nothing's changed there. Okay, next, what's our initial starting point? Well, our initial atmospheric pressure, they told us, was 101 kilopascals. Now, we have to find our decay factor because we're talking about exponential decay. Remember, if you look back in your notes, when you deal with decay, you're taking 1 minus your percent as a decimal, okay? So 11.5% as a decimal, okay? Move your decimal place 2 to the left. You're going to have 0.115, which is going to give you 0.885. So we're going to put that as our base, okay? And we're going to raise that to the x power still. Now, remember, we're using it to estimate the approximate pressure at a certain altitude. So we have to look at our initial altitude and the altitude we're at now, okay? All right, that's all I have for you guys today. You guys are going to get worksheet number 1. It is completion points. We'll go over it on Monday. If you guys have any questions, feel free to ask. The most importantly, make sure you guys are using the formulas that you're given and substitute your values into the correct places for your formulas, and you should be golden. All right, have a wonderful weekend. That's all for today.